Okay, here's video 2 of the notes. Sorry it's so long. We have a lot to get through in this section of the notes, but we're going to determine the order of each reactant. We're going to write the rate law expression, determine the value in units of K. So the rate law expression is going to be the rate is equal to K times the concentration of the reactants raised to whatever order they are that we determine from the data. Remember, the coefficients have nothing to do with whatever their orders are. It has to be experimentally determined by a set of data. So we got to see, how does a change in the concentration of A affect the rate? Does it not affect it at all? If we double A, does it double the rate? If we double A, does it quadruple the rate? If we double A, does it raise the rate times 8? We got to see that. So you got to look for experimental trials where the concentration of A doubles, but B does not. We need to keep that variable constant. So I noticed that between 4 and 5, the concentration of A doubles. How does that affect the rate? Well, the rate went up by a factor of 4 times as much. So this tells us that A must be second order, because if you increase the concentration of A, so for example, if the concentration of A raised to its order will tell you how much the rate changed, then the concentration of A doubling raised to whatever order it is, that's what we're trying to find, will make the rate go up by a factor of 4. The order must be 2. 2 squared equals 4. So A is second order. All right, let's see what order B is. So looking for trials where B changes but A doesn't. You can look at between trials 1 and 2. Concentration of B doubles. A stays the same though. How does that affect the rate? Well, it looks like the rate also doubled. So if we think about how the concentration of B raised to its order affects the rate, well, we doubled the concentration of B, and that made the rate also double, so the order has to be first, because 2 raised to the first power is 2. All right, so now we have the rate law expression. Now we know that A is second order, B is first order. We can finally determine the value in units on K. We can choose any trial you want. We have to just plug in the data and solve for K. Usually I just choose the first experiment because that's at the top and that's easiest for me to look at. So the rate is 0.01. That's going to be equal to K, what we're trying to solve for, times concentration of A raised to the second order times concentration of B raised to the first order. To solve for K, divide both sides. K is a big number, 10 million. Now, let's think about the units of K without looking up top. So this overall reaction is third order because 2 plus 1 equals 3, right? So the reaction is third order. Now, we know that K always has seconds to -1 and molarity to the negative something. That something is 3 minus 1, 2. And we can support that by, instead of plugging in numbers to the equation, plugging in the units for each variable, right? So rate is molarity over seconds. K is what we're solving the units for. A is molarity, and it's to the second order. And B is just molarity raised to the first order. Molarity squared times molarity is the same thing as molarity cubed. To solve for K, we have to divide both sides by molarity cubed. So that's molarity over seconds times 1 over molarity cubed. Molarity divided by molarity cubed is 1 over molarity second. So molarity to the -2, seconds to -1. Maybe pause the video, try to figure out the rate law expression, orders of C and D, and K on your own. I'm going to go through it now. So we know the rate is going to be equal to K times concentration of C raised to whatever order we determine it to be, times concentration of D raised to whatever order we determine it to be experimentally. The coefficients have nothing to do with the order. We have to determine the orders with experimental data. So I noticed that between trials 1 and 2, the concentration of D doubled, but C stayed the same. Let's see how that affected the rate. Looks like it also doubled the rate. So that tells us that D is first order. Let's look at C now. Between trials 4 and 5, C doubled, but D stayed the same. Let's see how that affected the rate. It didn't change it at all. It's the same. So 2 to what power makes the rate stay the same? 2 to the 0 power. That tells us C is 0 order. It doesn't affect the rate at all. Its change in concentration does not affect the rate at all. So you can leave the rate law expression like this. Let me clean this up a little bit. This should be 0 and this should be 1. Or you can drop the 0 order C because anything raised to the 0 is 1. So you say rate is equal to just K times D. Either or works. All right, there's a few other questions. What is the rate when the concentration of C, I forgot. We have to solve for K. So choose, again, any experimental trial that you want. I'm going to choose the first one, solve for K. So the rate is 0.02. K is what we're solving for. And the concentration D is 0.01. So we should see that K must be 2. Now, if we were to determine the units on K, this is a first order reaction overall. So we know that K is going to be seconds to -1 and molarity to something. Well, if this is a first order reaction and 1 minus 1 equals 0, that would be like molarity raised to the 0 power, which is just 1. So you can put it there or you could take it out. The units on K should be seconds to -1. We could also determine that by plugging in the units instead of numbers to the rate expression. So if the rate is molarity per second, K is what we're solving the units for, and concentration of D is in molarity. Well, if we divide both sides by molarity, that would be essentially molarity divided by molarity cancels out. The units on K is 1 over seconds, or seconds raised to the -1. Okay, what is the rate when these are the concentrations of C and D? This is literally just a plug and chug problem. You're just plugging in your value of K that we now know times concentration of D, and it's first order. The concentration of C isn't included because it's 0 order. So that tells us the rate has to be 0.96. And you see the units of the rate is molarity per second, or you could say molarity times seconds -1. All right, what happens to the rate when C is doubled and D is cut in half? Well, they didn't really give us numbers to work with, but we can still plug in our own numbers. So the rate is equal to K times D. So if D is cut in half, I'm going to just plug in 1/2 into D and think about how that would affect the rate. The rate is K times K. Rate is equal to K times 1/2 raised to the first power. Essentially, that would affect the rate by just cutting it in half as well. The concentration of C changing doesn't even matter because it's 0 order. It's not part of the rate law expression. In fact, if you were to put in 2, like doubling it, I'd plug in concentration of C as 2, but it's raised to the 0. That's just 1 anyway. So the rate would also be cut in half. Whatever we do to something that is first order, the rate does the same thing, right? If we double D, it doubles the rate. If we cut D in half, it cuts the rate in half. It's first order. All right, again, maybe pause the video, try this one on your own. I'm gonna go through it now. So we know that the rate is gonna be equal to K times the concentration of reactants raised to whatever power we determine them to be with the data. If we notice F doubles, the rate goes up by a factor of 8. 0.16 is 8 times bigger than 0.02. So we didn't really necessarily see this yet. So the concentration of F doubled, and that's raised to whatever order it is, which we're trying to determine. And that made the rate go up by a factor of 8. So 2 raised to what power equals 8? 2 to the third equals 8. So that tells us that F is third order. Let's figure out what G is. So I noticed that G doubled from trials 4 to 3, but I can't use that because F also changed. However, I noticed that from 4 to 5, G doubled, and F stayed the same. So let's see how that affected the rate. Looks like it made the rate go up by a factor of 4. So 2 raised to what power equals 4? 2 squared equals 4. That tells us that G is second order. Now that we have the orders, we can find K. So plugging in the first trial, and solving for K. We get K is 125,000. Now the units. This is a 5th order reaction overall. So that must tell us the units are molarity to the -4, seconds to the -1, because 5 minus 1 is 4. You could also find that by plugging in the units. So molarity over seconds is equal to K times molarity cubed times molarity squared. That's molarity over seconds equal to K, molarity to the 5th. If we divide both sides by molarity to the 5th, we get this. Well, molarity divided by molarity to the 5th is 1 over molarity to the 4th. So hence molarity to -4, seconds to -1. All right, last question. What happens to the rate if both F and G are tripled? Okay, so rate is equal to K times F, which is third order, times G, which is second order. They don't give us numbers, but since the F and G are tripled, I'm going to plug in 3 for the concentration of F and 3 for the concentration of G, and think about how that would affect the rate. Okay, so if I take 3 cubed times 3 to the second, we should be able to figure out how that would affect the rate. My calculator says 243, so that means the rate is 243 times faster, bigger. All right, that concludes these notes. If you're in Mrs. Kopas's class, I'm gonna have just a quick formative assessment. It's basically your learning goals, just you're answering them online. I just want to make sure that you guys are understanding this material before we move on. So if you could just complete that question online so I can see how you guys are doing, that'd be great. Thanks. Continue working on that homework packet as well.